Let's talk about recursion. So recursion is usually kind of hard to wrap your mind around, or at least it is for me, and it is for a lot of people. I tend to find it to make the most sense when I'm looking at math, and so I'm going to start off by introducing it that way, and then we'll look at it in code. So examples of recursion in math are something where it's going to do the same operation over and over and over again, but with a different subset each time. So for example, let's look at 5 factorial. So the definition of that is going to be 5 times 4 times 3 times 2 times 1. And likewise, 6 factorial is going to be 6 times 5 and so on and so on. I can literally just copy paste this over here. And then n factorial as a generic way would be n times n minus 1 times, and we could write this out as much as we want, dot dot dot, times down to whatever these are. So no matter what the number is, it just starts at that number and counts down each time we're multiplying every item in that row. So another way we could look at this is saying, what is 5 factorial? Well, if we look over here, 6 factorial, let's look at it as 6 factorial. Oops, I did not mean to zoom in a whole bunch. So let's look at what is 6 factorial. Well, over here, it's 6, and then I copy pasted everything from 5 factorial. So technically, 6 factorial is equal to 6 times 5 factorial. And we can define it in that way. So then the way this works recursively is we'd say, okay, but what is 5 factorial? I don't know what that is. Okay, so we define 5 factorial. 5 factorial, similarly, is going to be 5 times 4 factorial. Okay, but what is 4 factorial? 4 factorial is equal to 4 times 3 factorial. And this is going to sound really repetitive, but I find it's really useful to go through this entire thing. 3 factorial is 3 times 2 factorial. What is 2 factorial? 2 factorial is 2 times 1 factorial. And we could go down to 0, or we could define just straight up, what is 1 factorial? Well, 1 factorial is going to be 1. We could just say that. So this right here, this ending spot, is something we need in all of our recursive solutions. This is a terminating case. And a lot of the time, this is a case where we've broken down the problem as far as it will go, and we have to define what it is at some level. So 1 factorial, well, we're not really going to do 0 factorial. We could define 0 factorial because that's also just 1. So we could define both of these as terminating cases in the case that maybe we were asking what 0 factorial is. Or we could say 1 factorial is 1 times 0 factorial. That would also work. That would just give us another step. So 0 factorial is equal to 1. So then that could be the terminating case. And from here, we have our terminating case. And now we have a definition for this value. And we can start coming back up and subbing that value out. So instead of 0 factorial, we can say, okay, this is just 1. So 1 factorial now is equal to 1 times 1, and that's just 1. Okay, now we know what 1 factorial is. We come back up here, gonna get rid of that. We know 1 factorial is 1, so 2 factorial is 2 times 1, so it's 2. Now we know what 2 factorial is equal to. 2 factorial, we sub this out. We're going to put 3 times 2. 3 factorial is 3 times 2, which is equal to 6. That's what 3 factorial is equal to. Come back up here, replace this with 6. 4 factorial is 4 times 6, which is, I think, 24. We can double check that really quick. That is 24. Mark that out. 5 times 24. I'm not going to be able to do that one very quickly in my head, so we'll just do it here. That is equal to 120. Okay, 5 factorial is 120. And then up here, scribble that out. 6 times 120 is 720. And so that's what 6 factorial is equal to. So we've basically broken down the problem of what is n factorial, whatever we're asking about. It's equal to n times n minus 1 factorial. And then we keep going down until we get to the lowest level we can. And then we start returning those values back up. Okay? So this is the terminating case. This is where we end. But anytime we have something where we had a question, like what was 4 factorial, then that would be, when we're recursing down, a recursive case. And this also applies with programming, but let's look at this in some code. So I will go ahead and create a project. Okay, so let's define a function that does this same thing and breaks up our factorial into recursive steps. So factorial, and it takes some value, and in the generic version we talk about n. So the user is going to enter an n value. We'll have a result, so equal to factorial time, passing in the n value. And then we think about when do we recurse and when do we terminate. So our terminating case was either we could predefine 1 factorial as 1, or we could just keep it as 0 factorial. We could have both. Sometimes recursive statements have 2 terminating cases or multiple ones. So if n is 0, then we just return 1. Or if n is 1, we just return 1 as well, because both of those factorial are 1. Otherwise, we're going to recurse. We're going to ask the question, or we're going to say, what is n factorial? And then we're going to return n times n factorial. So this part is how we're recursing. We're going to say, return n times the factorial of n minus 1. So this is n times n minus 1 factorial. We just can't write it with this exclamation point here in C++. So then we're recursing. And let's add some cout statements, or we could step through with breakpoints, but let's go ahead and add couts just so we can watch it kind of operate. So we'll say n is n. Let's add a little line here, just so we see when every time it starts through. So we'll output term 1 for both of these. And over here, we can split this up so we don't return immediately. Let's just say int, let's say n minus 1 value is factorial. We'll keep this as return it with a comment out so we can keep referencing that. Factorial n minus 1. So we can also output recurse returned in 1 value. Int result is n times in 1 value. Result. And then we return the result. So I've just taken this part and expanded it into different steps so we can output each one. And we can go ahead and build and run. So let's look at 3. So n is equal to 3. We'll notice that it's not actually displaying anything else after it. It enters, n is 3, skips these parts. It is calling this part next. So we don't get any more results here. It's calling this, and immediately it comes back and says n for 2. Factorial of 2, again, comes through here, gets to this line, does not continue because it calls this function again with 1. So then we have factorial of 1. It's a terminating case, so we are returning 1. This part is actually from n equals 2. This part is from n equals 3. So let's also just output that here too. And sometimes I like to make these tabbed over. Did that not output what I wanted? Oh yeah, it's because it comes before here. So let's output that right there. Okay. So here's N1, terminate, N2, result of the previous one was 1, result is 2, N3, result was 2, now it's 6, and so the final result down here, which I forgot to output, is down here, so that would be 6. I'm going to add something just to make it easier to read this. So I like to also put int level, and that's just going to be something that lets us tab over a little bit. So for instance, we can output string, let's say level, and then just maybe spaces, and that will give us one additional tab or, you know, space over however many levels we're in. And this just looks nice because it can kind of help us visually differentiate what the values are. So we're going to do that. And I'm just adding level plus 1 anytime we recurse. So then at first we're at, let's say, 0, no tabbing over. The first recursion in is going to be level 1. The second recursion is going to be level 2. So let's make sure, oh, I did that wrong. Let's double check to make sure this looks nice. Now the code doesn't look as nice, but the output should look a lot better. So let's say 5. Okay, now we can see here's N5. It had to recurse. It's terminating. It returns back to N2. Here's that level. Returns back to N3. Here's that level. Returns back to N4. Here's that level. And returns back to N5. Here's that level. And then if we really want to display everything, let's say n-1 factorial is that. Result, let's say string level space. N times n-1 factorial is equal to, and we'll just output what n is, and times n-1, which is our n1 value. And we'll just put equals, and we'll put the result at the end, just to make it all on one line. So let's look at this again. 6. Okay, so we recurse in, we're terminating with 1, so 1 factorial. Let's make this look at, let's say, n factorial is equal to that. So I like to have really clear comments. That's just me. Here we go again. So recursing in, 1 factorial is equal to 1. That gets returned. We're at 2 factorial. Let's go ahead and put that here as well, so that's more explicit of what we're looking at. We can put that down here as well. Let's say returned. And I know I'm doing all this formatting, and you don't have to worry about all this formatting, but I'm just doing it so we can see like the output the way that would be most useful. So 1 factorial is 1, so that returned. So we're back at 2 factorial. Now that makes it sound like it returned that. Let's just say continue. Okay. We're continuing 2 factorial. We found that n-1 factorial is 1. N times n-1 factorial is 2 times 1, so it's equal to 2. And in the math that we did, this line is equivalent to this line. Then it returns this 2, return 2, enters it right here. Continue 3 factorial, n-1 is 2, so 2 factorial was 2. 3 times 2 is 6, so that's this line. Over here, we have 4 times 3 factorial, so that gives us 24. That's this line. Then 5 times 4 factorial is 120. That's this line. And 6 times 5 factorial is 720. So that's that line. So we can kind of see how this moves in and then comes back out, and we get a final result. Now, if you didn't want to display all of that and just wanted it so that the user could get the result, let's just name this one verbose. I'm going to get rid of level here. We're going to get rid of all of these couts so we can see the original version again in its simplicity. Get rid of all this part. So if we did not want the verbose version, we could simplify this, and again, this is all of the code for this factorial. If it terminates, we return 1 for if n is 0 or 1, 0 factorial, or 1 factorial. Otherwise, we return n times n minus 1 factorial. Okay? So that's one example. Okay, let's think of another problem that's not quite as mathematical. Let's say we want to pass in or have a starting point in an alphabet and an ending point, and we want the return to be all the letters between that. A, B, C, D, E, F, G. So that should be what's returned. Now we could write this with a loop, and we can also write it recursively, but let's think about this recursively. So if we have a start and an endpoint, how do we set this up? So let's say this is run 1. We have A and G. We'll just say start and end as kind of a column. Well, and then we have a string. Let's just say we're building our string and it starts off as an empty string, just nothing in there. How do we break this down so that we have the same problem each time, but we're solving just a small amount of it instead of everything all at once? So let's think about this. We could start from A to G, and then the next step would be, okay, maybe we need to do B to G next. We're just kind of stepping forward the letter we're starting at. D to G, let's say 5, E to G. So G isn't changing because that's kind of our endpoint. That could give us a hint for what our terminating case is going to be. F to G. And finally, G to G. So this will be kind of our endpoint. This is going to be our terminating case. So we could write this so it steps from A to B to C to D, and each time it recurses, it can be something like whatever the name of the function is, start plus 1, and the same ending, because we don't want to move the ending, then it would never stop, until it would hit a Stack Overflow. So each of these, we just move this forward by a little bit. We can start with an empty string, but let's say we're just adding the starter onto it. So A plus alpha for B to G. Okay, this is going to be B plus alpha from C to G. This is going to be C plus alpha from D to G, and so on. So we're going to take whatever that value is, the starter, and add on what the subsequent item is going to be. And we're saying, what is E to G? I don't know what that would be. Okay, well, we'll define it here. And we keep going until we hit that end point. E, F to G, F plus alpha, G to G. And at this case, if our start and our end is the same thing, we'll just say, okay, we're returning G. That's what that's equal to. So in this case, let's move this over a little bit so we have more space. we, just like the factorials, we kind of work our way all the way down until we get to an endpoint. If it equals itself, so, you know, if start equals end, that could be our terminating case. We just return the start. And now we have G to G defined. This is alpha G to G. And that's defined. It is equal to G. So then we can start pulling these back up. So alpha F to G is equal to F plus alpha G to G, which is going to be G. Okay, now we have a definition for alpha F to G. Alpha E to G is going to be equal to E plus whatever F to G was. So in this case, it's F plus G. Okay, we can start seeing that string being built. Alpha D to G is equal to D plus whatever alpha E to G was. So in that case, E plus F plus G. And so on. So again, this is kind of in my way. Let's get you out of here. Put you up here. And as we keep going, we'll see the same thing. And I'm going to write it all out because it's just helpful to see that pattern. So finally, we get alpha A to G is equal to A plus everything before it. And there we go. There's our final string, A, B, C, D, E, F, G. So again, we have our recursive case, we have a terminating case. Let's look at what this would be like in the code. So over here, recursively, we'll do the short way first. And currently these return nothing, so we'll just keep these as empty strings, just so it doesn't complain when we run this. The user is going to enter a start and an end. I don't know if that might be a keyword. It might not like that. Yeah, it's okay. And we're going to need a start and a end in each of these. We could do the iterative one last. So with recursive, our terminating case is usually what we're going to write first. Recursive case. So terminating case, if the start is equal to the end, well, then we don't need to move forward anymore. We just return whatever that start or end value is in this case. Recursive case, well, we're going to return whatever our start value is, plus whatever the result of start plus 1 and the end value is. And let's see, start from char. Okay, I forgot the string part of it, but we can turn this into a string. So let's say string start. Oh, no, sometimes this is always annoying to mess with. I'll say build is equal to start, and then we'll just return build. And in this case, let's say build is equal to start plus that, and return build down here. So just kind of working around that string, character to string thing. But then that should be okay. Let's go ahead and test this out. We probably need to call this function. And we'll get our start to end. And let's see, string result 2 is equal to that. Let's do tab. I just like to make everything look nice. Okay, so that's the second one. The other two, the iterative and the verbose version, we have not done yet. So let's do A to, let's say K. Okay, so those don't get called, but here we have A to K. It builds those out. So we can take this again and make a verbose version. And I'm going to add a level in here as well. So we'll copy this whole thing. We'll do root 3. We'll do the verbose version. And we'll pass in 0 as the starting level. So we'll just modify this. We are going to say, what is, let's say, string level and spaces. We are calling alpha, and let's just say start and end. Okay, terminating case. Let's just output string level empty terminating case equal to whatever that build string has. Down here we have recursive case. Let's just again split this into steps. So recursive result is equal to this whole thing. String current is equal to start, and then the build is equal to current plus the recursive result. Okay, so we'll output down here alpha start plus 1 to the end, oops, is equal to whatever that recursive result was. Down here, we'll output level space return current plus the recursive result, and then hopefully that will look pretty clean. So alphabet recursive, need to call this version and pass in the level, so level plus 1. Build does not like that because we have the starting one. We have the same issue here. Let's just output start here, and then it's built in down here anyway. Okay. String blah is equal to blah plus, what was it? What is it not liking? Current. Oh, nope. Never mind. So we'll set that there and build and run. So we'll do A to K. And now we can see every time it recurses. So we call alpha A to K. It hits this part. It needs to find whatever B to K is. Then it's going to call B to K. Now it needs to find C to K. So it's going to keep calling that over and over. It finally hits K. The end and the start match. So K to K is equal to K. Then it says, okay, J to K is equal to K. And it looks like for some reason it's outputting the ASCII values now. So let's update this a little bit. We don't want the ASCII value. We want this as a string. Let's see if we can get that to output correctly. Okay, let's try a char A to K. Okay. So then J to K is going to be J plus K to K. I to K is going to be I plus J to K. H to K, H plus I to K, and so on and so forth. Now I'm just rambling gibberish. So finally, the alpha from A to K is A plus the alpha from B to K. And so that builds the rest of this string, and our result is here. So this is outputting all this kind of nicely. This is the simplest, most just small, concise version. And let's think about what is the iterative case. So we could also implement this iteratively, but sometimes I find it makes it confusing if you think iteratively and then recursively. It makes it harder to think recursively. So we're going to just do it this way, where we're doing iterative at the very end. So over here, let's have our string build again. In this case, we can just iterate. So we can say for char, let's say letter is equal to the start, while letter is less than or equal to the end, and then we'll add 1 to the letter each time. Build plus equals letter, and return build. that builds and runs. Let's do A to Z. Here's the verbose one, here's the recursive, and here's the iterative. So they all give the same value. Now, this one, maybe it took a lot less thinking in terms of how to actually do that. We had to think of how to break it down for the recursive case, what was the terminating case, we had to kind of think in a different way. Why would we ever use recursive? Well, there are some specific reasons that recursive works when iterative would be a huge mess, or probably close to impossible to write something iteratively. For a lot of these introductory ones, this is more just kind of practicing how to think and how to break it down a problem into a recursive form. So let me find my notes over here. So if we were thinking of iterating through a file system, well, how would you really do that? It's much easier to think of a file system in terms of, here's a bunch of folders. Okay, display all numbers, or so it's easier to say, here's a bunch of folders and files, display all the files, and then go into each folder. And then each folder, display all the files, go into each folder. Go into folder, go into folder, and so on. So we treat each folder like we're recursing into it. That's what's on the desktop, there we go. What's in the documents, blah, blah, blah. So then it would recurse through each one of these. So as an example here, we could start at the C drive. If we're saying, okay, display everything inside of C, well, then we look at the work folder. Okay, recurse into the work folder. That's done, we return back to C. Okay, next folder is school. Okay, we need to display everything in C, including subfolders, so we have to recurse into school. School has the 2 subfolders, so it has to recurse into CS210. It displays what's ever in there, returns back to school. Next one is CS235. It recurses into there, and it comes into here and finds, this one's for a find algorithm, so it found what it's looking for, and it returns, and it returns, and it returns. So recursing through a file system is much easier than writing anything for like trying to iterate through it. Another way we can do this is we could backtrack. So let's say we have a little dude going through a maze, and it has some logic to just take a path, but if that path doesn't work out, it's going to start returning. So just like how our recursion returns, our little dude's path will forward, 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 forward. We kind of recurse to go forward in whatever direction we can. And if a direction doesn't work, we return, 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 and then continue on the next path. So we basically kind of do a partial recursion, or we keep recursing this way, and then we undo some of our recursion and then continue recursing in a different way. So we can use recursion to navigate in that manner.